Depth first traversal is one of the fundamental algorithms in software engineering that is used to explore and process data structures like trees and graphs. In the last video, we had looked at breadth first traversal. That was again another fundamental algorithm. Depth first traversal is a systematic way of visiting each element or node in a structure, going as deep as possible along one branch before backtracking. Let's understand this with an example. In the depth first traversal, we start at root node. So in this particular graph, we start at a root node. Let's say we start at 1. We can consider 1 as the starting node or root node. We would process 1. Once 1 is processed, we would move on to a branch of 1 that is not processed yet. So let's say 2 is not processed, so we would continue with 2. At point 2, we process 2, and then we move on to one of its branch that is not processed, that is 4 in this case. And similarly from 4 we would go to 11, and at point 11, since 11 doesn't have any child, we would backtrack. So 11 would go back to 4. 4 will look if it has any branch that is not processed. Since it doesn't have any branch that is not processed, it would backtrack to 2. At point 2, at node 2, we have another branch which is not processed yet, and that starts at 5. So from 2 we move on to another branch that is 5, and then we move on to, let's say, 10, and then from 10 we move on to 6. From 6 we move on to 3, and at point 3 we move on to 7. At point 7 we move on to 9, and since 9 doesn't have any child, we backtrack, we move back to 7, and 7 has another branch at 8, so we process 8. So the sequence of processing looks like this. Let's now look at how we would achieve it through the implementation. We would need a stack. Stack is a last in first out data structure. So whatever branch we choose, we want to continue with the same branch, and we want to go in depth, right? So that's why we are using a stack, so that once we push neighbors of a particular node, we can then continue from one of those neighbors, and then again we would push neighbors of the neighbors into the stack, and then we would pick yet another neighbor. That way stack would help us going as deep as possible along one branch, visiting a neighbor and then neighbor's neighbor and the neighbor's neighbor before covering all the neighbors of a particular node. We would start at node 1, we would mark it as visited. Once we mark it as visited, we insert it into the stack. So 1 is at the top of the stack. Algorithm says like loop through the stack till the stack is not empty. In every iteration, we would pop the top element, that is in this case 1. We would pop 1, we would process 1. So let's say processing is shown as blue. Then we would insert the child of this particular node. So whatever node that we processed, we would insert its children into the stack. So we would insert 2 and 3. So let's say we insert 3 first. So before inserting, we would mark 3 as visited. Then we would insert 3. And then we would mark 2 as visited. We would insert 2. Right? Next, we would look at the top. Top is 2. We would pop 2. We would process it. So it becomes blue. And at this point, we would insert its children. We mark 5 as visited. Insert 5 here in the stack. Mark 4 as visited. Insert 4 into the stack and move on. At this point 4 is at the top. We would pop 4. We would process 4, and we would also insert its children. Now at the top we have 11. We would pop 11. We would process it. Since 11 doesn't have child, we would backtrack in theory, but using stack helps us with it. So in a stack, at the top is the element that would be visited next if we backtrack. So here we would have backtracked from 11 to 4, 4 to 2, and then we would have gone to another branch from 2, that is at 5, starting at 5, right? So we can see at the top, we can see 5 here. In the next iteration, we would pop 5, we would process it, we would insert its child, that is 10. But before inserting, we should also mark it as visited. So now at the top is 10, we would pop it, we would process 10 and insert its child. We would mark 6 as visited and insert 6 into the stack. 6 is at the top, we would pop 6 from the top, process it, and then look for the children that are not processed yet. In this case, 3 is already in the stack, so 3 was already marked as visited, so 3 won't be inserted again. But since 3 is at the top, we are anyways going to process it. 3 will be popped, we would process 3, and then we would insert the next element, that is 7. We would then process 7, insert 8 and 9. Top is 9, we would pop it, we would process it, then we would move on, we would pop 8, we would process 8, and at this point there's no other element left. So at this point, when the 8 was popped and processed, in the stack there was no element, so the top didn't point to any element, and that is the exit condition for depth first traversal. Let's look at depth first traversal for binary tree. For trees, again we would start at the root node. This is how the depth first traversal would look like. We would traverse 1, we would pick one of its branch, let's say 2, we would process 2, and then we would move on to yet another branch of 2, that is 4, and then the branch of 4, which is 15. At 15, we know that 15 doesn't have any other branch, like any other child associated, so it backtracks to 4, and then from 4 we look for another branch of 4. So we go to 14, and then at point 14 we don't have another branch of 14, so we backtrack to 4, and 4, since 4 doesn't have any branch left, it backtracks to 2. 2 has another branch left, that is at 5, so it processes 5. Next is 13, and then 12, and then at 12 we don't have any other child, so it backtracks to 5. 5 doesn't have any other branch, it backtracks to 2. 2 doesn't have any other branch left, so it backtracks to 1. 1 has another branch at 3, so it processes 3, and similarly we move on. This is how depth first traversal happens in binary tree. Code for depth first traversal. Consider this graph as an example. This is implemented using the code over here. The explanation for this code can be found in one of the earlier videos. This is how the code for depth first traversal looks like. It is very similar to the code for breadth first traversal. I had explained that in an earlier video. Here we can see in the depth first traversal, it takes in graph and the starting node. It then initializes a stack. As we saw in the earlier demonstration that we would need stack to perform depth first traversal, so we are initializing a stack. I'm using Python list to perform stack operations. Next we would initialize a set for visited. In the beginning we would insert a starting node to visited to mark it as visited, and then only we would append it to the stack. So appending is more like pushing into the stack, and then we start the loop. It runs while stack is not empty. In each iteration we would pop from the stack. So popping means here we are not passing any index, unlike the queue implementation. So if we don't provide any index here, it would pop the last element. So this is more like last in first out, so it would get the last element that was inserted in that particular stack, and it would keep it as current node. Next we would process this current node, and after processing we would push all the neighbors of that particular current node. So we would get all the neighbors, we would iterate through neighbors, and we would see if the neighbor is not visited, and then only if the neighbor is not visited, then only we would mark it as visited and push it to stack for further loops. So the depth first traversal for this particular graph looks like this. Next we can start from 6 and see that since 6 is not connected to any node, it just traverses 6. We can also start from some other node, let's say 2, and we can see 2, 4, 5. It started from 2, it went to 4 and then 5. If we started at 3, we would see 3, 5, 2, 4, right? So 3 to 5, 5 to 2, 2 to 4. Let's look at space and time complexity for depth first traversal. For depth first traversal, space complexity is O of n, where n is the number of nodes in the graph. This is because we are initializing visited. Visited is a set of nodes that were visited, and in the worst case, when we complete the whole traversal, all of those nodes will be marked as visited, which means they will be part of the set. So the set's size will be n. And at the same point, stack is also the data structure that would grow proportionate to number of nodes n. Time complexity is O of n plus e because we would traverse each node once, and we would also traverse all the edges once, agnostic of whether the node that this edge is pointing to is already visited or not. That's the reason it's O of n plus e or O of v plus e, where v is the number of vertices. Thank you.